Welcome to sitza.com. Reduction of aldehydes and the ketones. Aldehydes and the ketones, they contain a carbonyl group. This is the RCOX, and this X can be hydrogen or the alkyl. When it's hydrogen, it's an aldehyde, and when it's the R, it is a ketone. So that means aldehydes and the ketones, you can reduce them by using different reducing agents into alcohols and also into alkanes. Depends what type of a reducing agent we use. So aldehydes can be converted into alcohols, or you can convert them into alkanes. It depends what type of a reducing agent, what reduction conditions we use here. So let me take here an example. If I take the molecule CH3COH, this is an aldehyde, I can reduce it into the alcohol, which is a CH3CH2OH. This is ethanol, by using any of the reducing agents, like for example you can use hydrogen gas in presence of a nickel, right? Or we can use also another reducing agent, a very famous reducing agent, which is lithium aluminum hydride. Okay, you can use this one also to convert this aldehyde into the alcohol, or even we can use the sodium borohydride, NaBH4. All right, this is the sodium borohydride is a little bit milder reducing agent than the lithium aluminum hydride, but all these reducing agents here, they convert the aldehydes into alcohols. Even if you have a ketone, it can convert it into alcohol. So from here, this is aldehyde, you get a 1 degree alcohol here, right? But if it is a ketone, like you have acetone here, you have CH3 C double bond O CH3, and if we use any of these above mentioned these reducing agents, we can convert it into the you can convert the C double bond O group into CHOH, right? It will be now CHOH, the middle one, right? This carbonyl group, and then there are two groups attached to this one also. All right, so that means you can convert a ketone into a alcohol. This is a secondary alcohol here, right? And this one is a primary alcohol. So from aldehydes, by the reduction of aldehydes, you get primary alcohols, and from the reduction of ketones, you get a secondary alcohol. And these are the reducing agents. You can use any of these reducing agents here. You can use suppose the lithium aluminum hydride, or you can even use the sodium borohydride for this conversion, or you can use the hydrogen gas in presence of nickel or platinum or palladium, right? Like these catalysts here. You can also get from the aldehydes and the ketones, you can get alkanes also, right? That means we can get alkanes, but not by these reducing agents, right? We have to use a different reducing agent here to get a alkane from the aldehydes and the ketones. We convert the aldehydes and the ketones into alkanes by two important reactions. One is a Clemmensen reduction, the other one is the Wolff-Christian reduction, right? Okay, Clemmensen reduction and the Wolff-Christian reduction, these are the two famous reactions from which you get an alkane from the aldehydes and the ketones. And here in this Clemmensen reduction, basically this is a very simple reduction. You can use here a carbonyl group, and you can use zinc mercury amalgam, zinc mercury and the hydrochloric acid. And in this, when you use this reducing agent here, zinc mercury amalgam here, and you can convert this carbonyl group into CH2. Basically you remove this oxygen with the hydrogen and you get the water there, right? So this oxygen from the aldehydes and the ketones is lost as the water. Let me take here an example. Suppose you got here the CH3 C double bond O CH3 here. So if you react it with the zinc mercury amalgam here, zinc and the mercury amalgam and the hydrochloric acid here, so what you will get, this carbonyl group here, it is converted, this C double bond O is converted into CH2, and the two groups attached to this carbonyl are CH3. So you get a CH3 here, and another molecule is CH3. That means you get a propane from this acetone molecule with the loss of water, and this is called as a Clemmensen reduction, right? In a Clemmensen reduction, this reduction involves the conversion of an aldehyde and a ketone into alkanes using the zinc mercury amalgam here, right? Similarly, you can take acetophenone. If you have a benzene ring attached to the carbonyl, and it is also attached to the CH3. If we use again the zinc mercury amalgam here, zinc and the mercury amalgam here, and this is a very good reducing agent, and it will convert this C double bond O into CH2. So you will convert the carbonyl group into CH2, and the two other groups attached to this carbonyl group are, one is the benzene, the other one is methyl. You also get in this reaction the water, right? Here the oxygen is lost as the water. Another reaction, similar to the Clemmensen reduction is that's called as a Wolff-Kissel reduction. That is a two-step process. Again, it also converts the carbonyl group into CH2, right? Okay, so this Clemmensen reduction converts the aldehydes into alkanes. We have another reaction, right? Again, this converts aldehydes and the ketones into alkanes. But this is a different reaction, right, than the Clemmensen. We use a different reducing agents here. Basically here in this Wolff-Kissel reduction, this is a two-step process, right? This is a two-step reduction. First we actually take the carbonyl group and we react with the hydrazine, right, NH2, and we have learned in the addition reactions of these aldehydes and the ketones that if you have a NH2 hydrazine, then first what happens, there is addition of a nucleophile on the carbonyl group, and then there is loss of water, and so you get here in this one you get a carbon double bond nitrogen. Okay, so after that when you treat it with the potassium hydroxide and the ethylene glycol and you heat it strongly here, then you convert this this group into CH2, and this nitrogen is lost as a Han2. From this molecule the two nitrogens are lost as N2. So basically this is, if you look at the starting compound and the final product, you see the carbonyl group is lost as water, right, from this from this molecule, and this converts into the CH2. So again you get a alkane, right? You get an alkane from the aldehydes and the ketones by a two-step process. First is reacting this carbonyl group with the hydrazine, and then treat it with the potassium hydroxide and the ethylene glycol, heat it strongly, nitrogen will be lost as N2, and you get an alkane. So basically if you take here an example, let's say suppose you got the CH3 C double bond O C2H5, this is a ketone. If you react it with the hydrazine NH2 single bond NH2, okay, what will happen, as we have learned previously in the reactions of these nucleophilic addition reactions of these aldehydes and the ketones with the hydrazine, this nucleophile will first attack on this group, the oxygen will shift, then one of the hydrogen from the NH2 will go to the it will go to the oxygen, and therefore it will form addition product. Once the addition product has been formed, then after that the water will be lost and you get this product. All right, that is the case that we have studied in our one of the videos where we were discussing the addition of the hydrazine to the carbonyl group, right? So finally what happens, first addition and then there is loss of water, correct? Let me write down here the addition product. When NH2 attacks on this electron goes here, so what do you get? You get a group like this. You got a CH3 oxygen, and this one has a C2H5 also attached to it, and now it will be the O negative, right? First it is the NH2 that will attack on the carbon, and then from the NH2 group one of the hydrogen shifts to oxygen, so it becomes OH, and then this is the C2, this becomes the NH2 here. All right, so this is the addition product that you normally get, and after that this addition product has been formed, right? Now what happens, there is a loss of water, right? This OH and the H is lost, and you get a carbon nitrogen double bond, and what do you get? You get an addition product like this, carbon double bond nitrogen. So you get a CH3 molecule, then a carbon, then attach it with the C2H5, and now there's a carbon nitrogen double bond over here, right? You have a double bond over here with the nitrogen, and then this is N and then NH2. Okay, so now what happens in this one? Now this is the addition product that you got when you react the this ketone with the hydrazine. You got this addition product. So now we react to this molecule, okay, with the potassium hydroxide and KOH and the ethylene glycol, right? Ethylene glycol, and you heat it strongly. What you will get, this nitrogen will be lost as N2 from this, from this intermediate, from this addition product. Nitrogen is lost as N2, so you get the carbon, CH2 group, right? Carbon attached with the hydrogen, so you convert it into the CH2. Then the two other groups attached to the carbon are, it is the CH3 and the C2H5. All right, so if you look at the starting compound and the final product, so look at this one, this is our starting compound and this is the final product. What do you see? You see that there's a conversion of this carbonyl group into CH2. That's the the net reaction. Okay, so once you first react with the hydrazine and then you react with the potassium hydroxide and the ethylene glycol, and you heat it strongly. The net result is that this oxygen is lost from here, and you attach the two hydrogen atoms. Means you are converting the aldehydes and the ketones into alkanes. So these are the two processes by which we convert the aldehydes and the ketones into alkanes. Wolff-Kishner reduction, and the other one is Clemmensen reduction. You can also convert the aldehydes and the ketones into alcohols by using the the different reducing agents like lithium aluminum hydride and also the hydrogen gas in presence of a nickel, right? So these are the different ways of reducing the aldehydes and the ketones. Hope you got the concept. Thanks for watching the video. Bye for now.